Hello, everyone. I am very glad to introduce our paper VQ-VLA, Improving Vision Language Action Models via Scaling Vector-Quantized Action Tokenizers. VQ-VLA is an innovative vector quantization-based action tokenizer built upon the largest scale action trajectory dataset to date, leveraging over 100 times more data than previous approaches. It demonstrates that action tokenizers can be effectively scaled by leveraging large-scale simulated action data. We prove that our action tokenizers improve the performance, inference speed, and long-horizon capabilities of VLA models. VQ-VLA pipeline is structured around two main, sequential stages. The first stage focuses on action tokenization. We begin by training a general convolutional residual VQ-VAE, Vector-Quantized variational autoencoder. This model is trained on the OpenX embodiment, Libro, and Monty-skill datasets. Once the VQ-VAE is fully trained, it is frozen and repurposed. It serves a critical role as an action tokenizer for the OpenVLA model, effectively replacing the simpler, less expressive binning method. In the second stage, with the trained VQ-VAE now providing action tokens, we fine-tune OpenVLA using the LoRa approach. The next step is real-world setup. For real robot experiments, we use a Franca Research 3-arm with a fixed RealSense D435 camera to capture environmental observations. We evaluate on 6 manipulation tasks, 4 short horizon, 2 long horizon, designed to evaluate the model's ability to handle varying task complexities. For each task, we collect 50 demonstrations and evaluate performance over 20 trials. Here are the real-world results. Adding synthetic trajectories significantly boosts the action tokenizer's performance, raising the average success rate from 23% to 46.25%, with notable gains in precision and dynamic tasks like flip the pot upright, a 30% increase, and pull out a tissue paper, from 5% to 20% plus. While the limited Libero dataset showed minimal impact on short horizon tasks, the much larger Monty-skill dataset led to substantial improvements. For long-horizon tasks, VQ-VLA, especially with VQO plus L plus M, dramatically outperforms baselines, achieving success rates of 50% and 30% on complex tasks where baselines struggle. This is largely due to VQ-VAE's ability to predict multiple actions per inference, reducing error accumulation and improving efficiency in long, sequential tasks. In the simulation experiment, to avoid potential performance inflation from in-domain data during evaluation on Libero 90, we trained the VQ-VAE action tokenizer on completely out-of-domain Monty-skill and RL-bench simulation data, rather than Libero data. The results demonstrate VQM+ are reached 80.98%, outperforming the OpenVLA baseline by 7.45%. During the real-world experiments, we measured the action execution frequency of VQ-VLA and compared it with the original OpenVLA. As shown in the table, with a compression ratio of 5 in VQ-VAE, the inference speed is nearly tripled. This significant improvement greatly facilitates real-time performance in practical applications. This is a one-time speed demo of the VQ-VLA real robot experiment. The actual inference speed is faster. Thank you for your attention.